So in the last class, we spoke about vibrations in 1D chain, and we spoke about monatomic chain, which means that the atoms on that chain are similar. That is, if it is carbon all through. All the atoms on that chain are carbon. So now we're talking about vibration of a diatomic chain. We'll still be talking in 1D, but diatomic chain in the sense that we have two different types of atoms on that same chain. And the atoms have can be said to have different masses. So atom A is having mass M1, atom B is having mass M2. And also the, unlike monatomic chain, where the spring constants of holding the atoms together, where they are the same. In this case, it's going to be, you are going to have two different types of, spring constants. That is the one holding M1 and M2 will be different, or to the right will be different from the one holding M2 and M1 on the right hand side of M2. So we're talking about M1, M2, and we also be talking about kappa 1, kappa 2. But to make analysis to be very simple, we can make any of two assumptions. We can assume M1 to be equal to M2, where we'll deal with, where we'll check the effect of having different types of kappa. We can also say, let kappa 1 be equal to kappa 2. Then we'll now have different types of M. That is, we'll be having M1 not equal to M2, but kappa 1 will be equal to kappa 2. So that's those are the two assumptions we can make. So the kappa here are spring constants, while the M are the masses. So just like we did in monatomic chain, where we spoke about the Newton's law. We spoke about the Newton's second law of motion by saying that F is equal to MA. By saying F is equal to MA, and we know that A is as good as the x square over the t square. So, and that is exactly what we have here. And also going to Hooke's law, we can say F is equal to kappa times extension. We say, and what is extension? Extension is change in length. And when we are talking about change in length, we are talking about dx. And so with the same method we used in, so this is the equation 321. Equation 21 is the equation that tells us, equation 21 is the equation that tells us the two equations we can have, which is having M1, the first Newton's law on M1, and the same thing, the force on M2. So having this, from this equation, we can decide if we want to make M1 to be equal to M2, or we want kappa 1 to be equal to kappa 2. So by doing that, the problem would be simpler. So in this scenario, you'll notice that from equation 21 to 22, we no longer have kappa 1 or kappa 2 any longer. So what we now have is kappa. So we have made kappa 1 to be equal to kappa 2, and we have made mass 1 not to be equal to mass 2. So by taking kappa 1 to be equal to kappa 2, we can replace all the kappa 1s and kappa 2 in equation 21 with kappa in equation 22. And that makes it a whole lot simpler. And now coming to the, just like we had in the monatomic chain, we also have a trial solution in equation 23, which you can differentiate with respect to time, twice with respect to time. You can also differentiate equation 23 with respect to distance where necessary. But for now, this is we're interested in the differential with respect to time. So when you differentiate this equation 23 with respect to time, and you now substitute it into equation 22, we are going to have equation 24. So to solve equation 24, the coefficients of equation 24 are inserted into to form a matrix. And for a homogeneous linear equation, such matrix should give us 0, which is equation 25. So when you look at this carefully, you'll notice that the coefficient of AX, sorry, let me bring out the pen. The coefficients of AX are in this column, while the coefficients of AY are in this column. So when you check this particular expression, the coefficient of, this is the coefficient of AX, and this is the coefficient of AY. And when you check this particular equation, this is the coefficient of AX, and this is the coefficient of AY. So this is equation 25 is solving equation 25. When you solve this determinant, you are actually going to get easy way out of determining the relationship between the wave vector k and the angular frequency omega. In some other way, if for us to arrive at this equation 25, we assumed that kappa 1 is equal to kappa 2 equal to kappa. If we had made the assumption such that kappa 1 is not equal to kappa 2, but M1 is equal to M2 is equal to M, we wouldn't have had this equation 25, we would have had equation 26. So this equation 26 is just there to help you in case you want to try to attempt this solution with the second assumption, which is M being constants, while the spring constants not being equal. So let's continue. So let's continue by saying our kappa is constant in equation 27. We are going to have two solutions, which are given in equation 28. The two solutions is relating, you can see that we are relating omega with omega is now related to wave vector, but in this case, we are going to see what's happening at this point at optical branch very soon. So when we were discussing about monatomic chain, we spoke about a dispersion relation, and that dispersion relation showed us the relationship between wave vector and angular frequency. But in a diatomic chain, the dispersion relation is different. In a diatomic chain, we have two different branches. Let me put it that way. Two different types of vibrations. One is referred to as the optical, while the other is referred to as the acoustical. And one of the major things we would notice about the difference between the two is that the frequency of the optical is larger than that of the acoustical. That is the first thing we should notice from here, because in this courseware, I have made M1 to be greater than M2, and and kappa 1 to be greater than kappa 2. So wherever we are saying M1 is not equal to M2, for this courseware, I've chosen M1 to be greater than M2. And in cases where kappas are not equal, kappa 1 is greater than kappa 2. So all the equations we have here, they are easily visualized on the graph, which we'll see very soon. So all those equations, you can look at them after the class. You would notice that this, okay, you notice this as omega optical, acoustical, and omega optical over there. So, and another thing we should also notice about this plot is that it is starting, the center is 0. The center is 0, and the boundaries, the edges are minus pi over a and plus pi over a. That means that the whole length here is 2 pi over a. And when it is 2 pi over a, that means that in one dimension, whatsoever we have as a in the direct lattice space gives us 2 pi over a in reciprocal lattice space. So we'll be talking about reciprocal lattice later on in the course. So, but we should just note that when we have a as direct lattice, its equivalent is 2 pi over a in reciprocal lattice space. And a quick way to not to confuse you is to think about direct lattice as what we can see, while the reciprocal lattice space is something that is abstract, an imaginary world. But that imaginary world, the understanding of that imaginary world helps us to understand what really happens in the physical world. If we have time, I would show you some real life practical applications of this direct and reciprocal lattice space. And that reminds me, I got an email from Levi telling me that whenever the time is up, I should leave the class. And I feel it's somehow awkward. And he sent the mail and he said he's sending it on behalf of everyone. And I had to reply, is he the class rep? And he's here to reply now about 2 weeks ago. I think it's somehow awkward. If normally in my class, you are free to come in at any time and leave at any time. So I don't know why somebody will be sending a message to tell me that whenever my time is up, I should leave. I think it's somehow strange. In my years of staying on this campus, I've not heard that in my whole year. I want to believe he's speaking for himself. If I would assume he's speaking for everybody, it won't be very funny. I'll just take it as he's speaking for himself, because I should not waste your time by reading out the mail. But I think it's very awkward. That's just the simple truth. Whenever the last week we couldn't meet because of public holiday, and that will be the second time in a span of about 3 or 4 weeks. When we meet, we have to meet 1 hour per week, and we are having public holidays even in weekends, and they put it on Monday. And somebody's complaint is to say that whenever my time is up, how long do I spend? The maximum is 30 minutes extra. And I don't, well, let's leave that one. But whenever the time is up, if you want to leave, please leave. And even if I see anyone bearing lever here, once it is 1 o'clock, I'll kick out the person. Okay. So some people, the life they live is a very wretched life. They are very poor. They cannot afford to even drink gari. But once they close their eyes to sleep, they become Dangote. They become very rich. They become a very big man once they sleep. So we can say people in that nature, in their real life, they are like A, but in their reciprocal life, they are 2 pi over A. When you look at this A, when you take A to be something like 5, and you take it also, hello, who is that? Okay, so when you say A is 5, and you also say A is 9, in the direct world, you can say 9 is greater than 5. But when you come to the reciprocal lattice space, it will be the other way around. That which is big here will become smaller. 9, which is bigger here, will become smaller when we come to the reciprocal lattice space. So as time goes on, we are going to apply things like that. So in the reciprocal lattice space, so in the direct space, we say that the lattice constant is A. But in the reciprocal lattice, the lattice constant is measured as 2 pi over A. 2 pi over A, meaning that from this edge to this edge. So when you have length A, it will be equal to 2 pi over A. And in the direct lattice space, you notice that the unit here is something like length. But in the reciprocal lattice space, the unit is 1 over length. So the measurement here is like measuring in the reciprocal lattice space is like measuring in units of K, units of wave vector, while the measurement in direct lattice space is measured in units of length. So this zero, the zero at the middle here can be said to be the center of the cell. So when we are talking about a cell in direct lattice space, in the reciprocal lattice space, we call it Brillouin zone. So a cell in a direct lattice in the real world is equivalent to a Brillouin zone in the reciprocal lattice space. And the length of a unit Brillouin zone is 2 pi over A. And you'll notice that this is what we add when we're talking about monatomic vibrations. We have just the acoustic mode. We have just the acoustic mode in monatomic vibrations. But now in diatomic, we have an additional mode, which is the optical. And when K is approaching 0, this looks linear. When K is approaching 0, this looks linear. And when K is 0, the frequency is 0. But for the optical mode, when K is 0, we have a non-zero frequency, even when the wave vector is 0. So the in the course where the items I put on the left here are the items where we made M at this end, at the right hand corner, we have M1 equal to M2 equal to M. Whereas on the left hand corner, we have kappa 1 equal to kappa 2 equal to kappa. So those are the both of them, they are actually whatever equation you find at this spot, this equation is equivalent to this particular one. The only difference is the conditions. And also this equation is equivalent to this. This omega optical is equivalent to this. But at the point where they agree, the acoustical, when kappa is equal to 0, it is 0. But at this point, these are the frequencies when wave vector k is 0. When wave vector k is equal to 0, we have finite non-zero frequencies. So from year to year, like I said, is one Brillouin zone. And we have the same equation, so the same figure 6 and figure 7, they are telling us the same thing. In figure 7, minus pi over a to pi over a is a Brillouin zone, while from minus 2 pi over a to plus 2 pi over a is also a Brillouin zone. So, but the inner one, which is close to the center, is called the first Brillouin zone, while the outer one is called the second Brillouin zone. So the second Brillouin zone seems to encapsulate the first Brillouin zone. So let's just save that in one part of our memory. Very soon we'll be seeing things that that resemble this in the future. And you should also notice that the acoustic mode, when it touches the boundary, this particular point is the boundary of the first Brillouin zone, just like we had in the figure 6. This edge is the boundary of the Brillouin zone. So the width of the Brillouin zone is 2 pi, which ranges from 2 pi over a, which ranges from minus pi over a to plus pi over a. And the center is 0. And you would all notice something here, a gap between these points. And so there is a particular frequency that do not tally with any wave vector. So we'll be seeing things like that later on. Let's just move ahead. So tight binding, this resembles what we did in when we're talking about covalent bonding. And in this case too, we consider a chain of molecular orbitals to represent a 1D solid, as it's a one-dimensional solid. Remember that this chapter is dealing with only one dimensions, because talking in one dimensions is simpler to analyze compared to higher dimensions. And when we understand the one dimensions, it is easy to extrapolate to 2 dimensions or 3 dimensions. So everything we have here is similar to what we have said before. This is like it's called Chronicle Delta. Whenever n is not equal to m, this would be 0. Whenever n is equal to m, the Chronicle Delta would be 1. So this is so we are assuming that there is a single orbital n on atom n, and that the system has periodic boundary conditions. We've done periodic boundary conditions in the past. All orbitals are orthogonal to each other, and this is the condition of orthogonality. So one orbital n must be orthogonal to m. The Chronicle Delta nm gives us 0. So, and this is a trial wave function, and the Schrodinger equation. And from the Schrodinger equation, we have the Hamiltonian, which is defined here to be the kinetic energy of electron plus the potential energies which of electron to nuclei. So when we have 5 nuclei on that chain, when we have 5 atoms on that chain, we can say that J is equal to 5. So, and we will check the interaction of the electron, the Coulombic interaction of the electron with each of the nucleus. So, and when we are calculating a potential, this is it is calculated as a function of, it's calculated as function of displacement. That is, this is r, small r is the position of the electron, while big R subscript J is the position of nucleus J. So R, small r minus big R, which are vectors, will give us the displacement, because V depends on this. So this is not V times, this is like a function of V as a function of R minus big R. Okay, so let's move on. So just like and if you follow what we did in covalent bonding, everything here should be straightforward. Then we spoke about atomic and orbital M, and we spoke about so yes, whenever n is now equal, this way we now consider is n equal to m or is n not equal to m. So when n is equal to m, we have V naught in equation 38. When n is not equal to m and n is not greater than m by 1, we would have 0. And but when we're talking about covalent bonding, we did not. It was either V naught or 0. So the T is the opposite term, which talks about the tendency of an electron to move from one site, that is from one nucleus. When an electron, we know that an electron revolves around the nucleus, and for an electron to move from one nucleus to the other, it is this term T, which is the open term, that accounts for such a move. And we don't expect it to travel more than the next neighbor. That is why we have 0 whenever n is neither equal to m or n is not less than m by a modulus of 1. So because of time, we have to rush to another topic, which is crystal structure. Must have heard of crystal structures, most likely in your secondary schools. Let me say GSS class, where we'll talk about sodium chloride crystal as a crystal. So, and crystals, in a simple definition, are regular repetition of identical structures. Regular repetition of identical structures. So when you have a pattern, so we when we're talking about crystal structure, we usually talk about lattice. Lattice are like imaginary points also in space. Lattice are like imaginary points in space, and when those points are occupied by atoms, they create what is called a crystal structure. So the lattices, the type of pattern that the lattices they form gives us information about the nature of the atom. So the type of, so there are some elements or some materials in which when they want to crystallize, they form things like that. When you look from the top, you see things like squares, like square dots. But some, when they want to crystallize, you still find one at the center here. So it depends. So it is not sufficient for us to just talk about the property of materials based on its capacities and some other electronic properties without talking about how they are arranged. So the arrangement of the atoms is what is called crystal structure. So is what we study under crystal structure rather. So the arrangement of atoms, and when we are talking about copper, for instance, if this were meant to be the crystal structure for copper, every point here will be occupied by copper. When some points are occupied by things that are not copper, then we can no longer call it a crystal structure, because when it is crystalline, the repetition will be the uniform. When you go to the left, go to the right, move up, move down, move in, move out, it will still be identical. And at this point, we can also remind ourselves to say that the distance between these points and the neighboring atom will be A, lattice constant. And that distance, before we forget, at the reciprocal lattice space will be 2 pi over A. We'll get there very soon. So, but just know that whenever we are talking about crystals, there are 2 different types of lattices. The direct lattice, which is the one that we see, we interact with, and also the reciprocal lattice, the one that looks imaginary, but very useful and helpful in understanding the nature of materials. So let's move on. Okay, so equation 1 here is telling us about translational vectors. Translational vectors in the sense that, let's make things simpler. Let's talk about 1D now. Let's have a 1D chain, and let's have atoms, and let's use numbers that we are used to. Let's say from this point to this point, it is called lattice parameter. The distance between these points is also equal to the distance here. That is what makes it a crystal lattice. The distance of separation between each of the atoms is the same, and called A, lattice parameter. And A is lattice parameter. We should also note that let's use a figure. Let's just say 2. Okay, let's use figure units where, let's say 2 centimeters. So we don't have anything of 2 centimeters in nature, but let's just say 2 centimeters. Let's say at this point, let's take this point to be our origin, 0. Then you'd agree with me that these points will be 2 centimeters. This will be 4 centimeters. This will be 6. This will be 8. And this will be 10 centimeters. When you have, let's assume this is like a graph. You want to plot a graph, and you have labeled your x-axis to be 0, 2 centimeters, 4, 6, and 8 centimeters. When an ant walks on this line, and the ant gets to this particular point, let's say this particular point, let's say the ant walks to this particular point, which is 2.5 cm. When the ant walks to this particular point, which is 2.5 centimeters, and the ant looks around and observe what is surrounding it. If the ant takes off, and moves by a lattice constant A. If the ant moves by a lattice constant A, that means that the ant would have traveled from this point to this point, which should also be called (4.5 cm). When the ant gets to this particular point and looks round, when the ant gets to this particular point and looks and turns around and observes how the environment looks, whatsoever that ant observes turning around should be the same as what it observed when it was at this point. So that is the work of this equation 4.1. And when we are talking about this illustration is like trying to talk about 1D. When we are talking about 1D, it's like a single line. When we are talking about 2D, it's like you working with your graph sheets. And when we are talking about 3D, and when we're talking about 2D, like your graph sheets, you have x-axis and y-axis. When we are talking about 3D, we have x-axis, y-axis, and z-axis. But there is also something a bit different to be trying to look at this point. When we are talking about a cube, for example of a cube is your seasoning cube, your seasoning cube or sugar cube. Your seasoning cube or your sugar cube has a shape of something like this. And from this point to this point, you can say length A. This point to this point, you can say length A. And also the height, you can call the height length A. When you want to describe this cube, you can say that it has length A on the x-axis, it has length A on the y-axis, it also has length A on the z-axis. Also has length A on the z-axis. That is very straightforward, easy to imagine. But there are also some cases where the length A of this, the first length A will sit on the x-axis, but the second length A will not sit on the y-axis. It may want to be slant. Imagine your graph sheet. This is your x-axis, but you now have another axis that is this way. You can't call this y-axis. This other line, you can't call it y-axis. You can call it a combination of, because as this line I've drawn here has both x components and y components. So we cannot really call it y. It is combination of x and y. But if this line continues like this all through your graph sheets, we'll be forced to give it a simple name. We'll be forced to give it a simple name. And that simple name could be anything, but whatsoever that simple name is, it should always remember that it is given birth to by both combination of x and y. So in this case, we can decide to label this axis as our A1 axis. And we can decide to label this particular slanting axis as our A2 axis. One thing you've not noticed about your graph sheet is that your x-axis is like a vector x. Your y-axis is like vector y. And the same thing is applying here. Our A1 here is vector A1. Our A2 here is vector A2. And I have tried to bolding wherever we have vector. When you look at this particular equation, it is saying R prime is equal to R plus U1, A1. If you look at this U1 and A1, A1 is bold. For the fact that A1 is bold, it's deliberate. A1 is bold because A1 is a vector. A2 is not bold because A2 is not a vector. So this is vector A1, this is vector A2, this is vector A3. So when we try to relate this equation, R prime is as good as this particular point where this ant walked up to. R here was the initial point where it was. So the initial point where that ant was is R. But for now, this equation, since we are talking about a one-dimensional space, it can be reduced to something like R prime is equal to R plus U1 A1. So for the fact that, and sorry, U1, U2, and U3 in equation 1 are integers. So our ant that we're talking about initially started at this point R. It moved a certain length A to the right. Length A here, if you recall, is 2 centimeters. It traveled 2 centimeters to the right. On getting to this 4.5 centimeter mark, on turning around, everything it observed looked as if it was at this point. So that is exactly what this equation is trying to tell us, that it moved one integer, exactly one integer of an integer of the lattice constant. It moved to the right. So A1 is like a lattice, can call it, I don't want to call it a lattice constant directly, but for this particular direction, if you have traveled A1, if you have traveled distance A in direction A1, then we can say that your total journey will be as good as U1 times A1. So when U1 is 1, that is when the ant travels from this point to this point. When U1 is 2, then we'll be talking about 6.5. When U1 is 3, we'll be talking about 8.5. So, and what is our A1? Our A1 from this expression is 2 centimeters. So as long as from this point, wherever you were at any particular point within the lattice point or within the crystal structure, when you take a certain distance, when you travel a certain distance from that particular point, plus integral multiples of each of the wave vectors, then you would have said to be in another spot that looks exactly like where you are coming from. So without wasting much of our time, the summary here is that U1, U2, U3, they are integers, and this just like I explained there, it's saying that we can call this axis A1, axis A2. Fine, we can call this axis X if we like, but it is wrong for us to call this the other one axis Y. But at least A2 can represent this particular. So we can take this to be an axis. And also in 3 dimensions, there are situations where when you imagine your seasoning cube or your chocomilo, or you imagine that it is no longer, when it is damped, when it has absorbed moisture, and you now press it, you can deform that shape such that the angles will no longer be 90 degrees. And when you deform it, it will it may have the shape of the lattice of a certain crystal structure. So we have, just like we have your sugar cube, where we can say this angle here is 90 degrees, the one here is 90 degrees, and also the one at this corner is 90 degrees. We have some other ones in which it will no longer be 90 degrees. And when it is no longer 90 degrees, then it is not your usual X, Y, Z plane. It will now have a name, and a convenient name, a conventional name, is to call them A1, A2, and A3. So as we move on, as you also try to, let's say, ruminate, I expect them to sync. So a crystal translation is defined in equation 4.2, and it's, if not exactly, very similar to what I've just told you. So when you have a certain crystal, let's try to draw, let's try to draw another crystal, yeah? Let's say, let me try to, let's make it a little more beautiful. We have the right to call this A1, to call this A2, and to call this A3. There is no strict rule to say this must be A1, that must be A2. So as long as we have this to be dimension A1, dimension A2, and dimension A3, when we have 5 of this, and we arrange them side by side, we can, this particular cell can be said to be like a building block for the entire crystal structure. So for the entire crystal structure, this particular A1, A2, and A3 are called the primitive lattice vectors. So when we have the primitive lattice vectors, you can decide to this U1, U2, U3, they are still integers. So you can decide to make this 1000, leaving this ones 1, 1. Then it's as good as you have arranged 1000 of these blocks to the right. And when you decide to also turn this to 10, you have, it's as good as increasing the height of this, arranging behind this particular cell, arranging as much as 10 behind it. And you decide to make U3 to be 3, as good as taking the layer you have, multiplying it by 3, making the one at the base to be the first layer, and now you're having a second layer and the third layer. You're having the second layer and the third layer. So any 2 lattice points within the crystal structure is connected by T. So for simplicity, you may want us to draw that our one-dimensional structure, where we call this lattice points. And at the lattice points, when you take this point as a reference point, and this A1, 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 when we say 3A1, 3 is an integer. 1, 2, 3, we'll find ourselves here. When we say, which is on the lattice point, when we say 2A1, 1, 2, we find ourselves on the lattice point. When we say 500A1, when we go further, we will find ourselves on a lattice point. That is all what this equation 4.2 is telling us. That is, when we are at a certain point, which is a lattice point, everything we have on this right-hand side will take us to another lattice point. That is all that equation is trying to say. And if you look at it closely, it's very similar to equation 1. And before leaving this introductory part, there are also some things we should tell ourselves, which includes that when you take a particular crystal and you turn it around, you are going to have it's called rotation. When you rotate a particular crystal, or let me say a particular cell, let's say primitive cell of a crystal, where you take a Maggi cube, you turn it around, it should give you exact same thing. That is where you turn it completely all around. Well, let's use a sugar cube, for instance. I think a sugar cube would make a clearer picture. When you take a sugar cube, you turn it all around. It can be said to have turned by 360 degrees. And 360 degrees in radius is what we have here as 2 pi. When you turn it by 2 pi, it is going to give you the exact same thing you had. When you turn it by half rotation, you're going to have the exact same thing. When you turn it by 1/4, that is pi over 2. When you turn it by 1/4 of a rotation, which is pi over 2, you are going to still have the exact same thing. So there are some crystals in which when you turn them by 120 degrees, which is 2 pi over 3, they are going to give you the exact same vision. So in nature, all these types of rotation, all these types of rotation, they are valid. But this 2 pi over 5 and 2 pi over 7 type of rotation, they are invalid. You can, when you turn a crystal by 2 pi over 5, it is not going to give you the exact same thing you had when it was at the origin facing you. And the same thing applies to 2 pi over 7. And when I'm talking about rotation, it is not just turning it anyhow, turning it at the center, at lines of symmetry. So turning it at the line of symmetry. So when we are talking about line of symmetry, it's like a line that goes through a particular material such that it assumes a central position. So and it can be from the center of the face. When we take a cube, for instance, the center of the face of one cube, when you insert a needle vertically into that cube and it comes out from the opposite face of that cube, you can be said to have a symmetry there. And when you rotate around that point, you can have exact what we are talking about here. So the rotation is not just any type of rotation, it is about the line of symmetries. And even in the very soon we'll get to lines of symmetries. Okay, this even right here. Okay, so this is what I was trying to explain just now. So when you insert a needle from the center of the face of a cube and it comes out outside, so when you rotate, when you hold this needle and you begin to rotate by 2 pi or pi over 2 or pi over 4, you should have the exact same visual of what you had. And the same thing applies when you rotate about this needle. So this symmetries, this line of symmetries, this is 1, this is 2, this is 3. They go through the face of the cube. So, and they are called the three tetrad axes of the cube. So what we have here is a plane that cuts the cube into half. And the plane is parallel to the face of the cube. And this plane cuts the cube into half, and the plane is aligns with the diagonal of the cube. And at the corners or the vertex of the cube, where you insert a needle such that it comes out through the opposite corner, it can also form a symmetry. And we can have, since we have 8 corners for the cube, or 8, I think it should be vertex. So since we have 8, it means we should have 4 triads. So those are the 4 triads. And also the cube also has 12 edges. So, and the 12 edges implies that when we also insert a needle at the center of each of the edge down through the opposite side, we can have through the opposite edge, we can have 6 of such, and each of them would also form symmetries, and they are the 6 dyad axes of the cube. So we're talking about lattice. These are lattice points. These are lattice points. These are lattice points, and this in 2 dimensions. And this also lattice points. You can see this resembles square lattices. So just like the ant illustration I was talking about earlier, when the ant is here and it moves 3x plus 4y from this spot, 1, 2, 3, 1, 2, 3, 4. When it turns around, it sees exact same thing of what it was seeing before having that translation. So I think it was here earlier, and it moved 1, 2, 3, and it also moved 1, 2, 3, 4. When it turns around here and it turns around here, it is going to observe the exact same visual by turning around. So, and even the environment, not just the visual, the property of at this point, electronic property or whatsoever property you want to talk about in the crystal at this particular lattice point is the same as what you will find on other lattice points. So the same thing applies here, though we can say that this point to this point here is our length A, and yet here is also our A. So we can cut out a box here to say this box should represent our building block, should represent our primitive lattice cell, and this block would build up everything. The primitive lattice cell or the unit cell, where you have 1 million of these, you can build as much as 1 million squares. So this when we have the knowledge of this particular cell, then we can say that we can tell you everything in this particular big cell. And the same thing applies here. The A here should be something like this. This is the closest distance. This is also A. So when we have this cell too, this is the building block that goes all through. And if we want to choose our cell, if we don't want to go that way, there are also some other ways. You can decide to take it this way. The area we have here, the area here should be equal to the area here. If I'm not mistaken, it should. So anyway you take your unit cell, as long as it is a unit cell, it will build up to give you the exact framework of what you need. Yep, okay. Okay, so at the base here, let me clone this off. We have a 3D cell. So the 3D cell, just like we spoke about that ant, when the ant comes here, and in this point, it's not going to be just A1 or into the A1 and A2. At this point, it will be A1, A2, and A3. And at this point, we'll be using equations 1 and equations 1 and 2. We'll be using them completely. So I expect you to put on your imagination ability to figure this out. So like I've said earlier, the primitive lattice cell or unit cell or primitive cell, whatever name you call it. This is an example here, a unit cell with this shape. You can see that it's not standing, this, we cannot call this y-axis. If you like, you can call this axis x-axis if you want. And x-axis here means that, you know, initially I told you that we are dealing with A1, A2, and A3. And I told you that A1, A2, and A3 are vectors, right? Okay, A1, A2, and A3, they are vectors. So since A1, A2, and A3 are vectors, A1 can be said to be a particular integer. Let's use integer j in the x with unit vector x plus k in the y direction plus l in the z direction. So this A1 is a vector. A1 is a vector. So when you look at this particular unit cell, fine, you can say that your A1 here should be something x-axis, fine. But this is your particular y-axis. This is the original y-axis. And this is having, so that means that this part, this line on the this axis, so we can, it's convenient to call this our A1 axis, but and this particular point, or this particular line rather, our A2 axis, and our A2 axis is having components of A1 and A2. Is sorry, it's having components of x and y. It's having component of x and y. So I'm sure you are not new to resolving the components of vectors. When you have when you know this to be, let's say, 5 centimeters, and you know the height to be 4 centimeters, it's directly you can determine this to be 3 centimeters. So in that case, we will not call it this length to be 5. We'll call it, if you like, you can say 3i plus 4j. If you like, you can say 3x caret plus 4y caret. So when we are talking about, we are talking in terms of A1, A2, and A3, they are vectors. And since they are vectors, they have the ability to have values in the x, y, and z directions. So the x, y, and z directions, they can, so it's not compulsory that this line stays on the y-axis. It has the right to be slant, and when it is slant, it is it's obviously having components of x and y. For the fact that it's having x and y, it will be wrong for us to just call this y-axis. So since it is wrong to call it y-axis, it is convenient to call it A2, which is a vector that depends on X, Y, and Z. So hopefully in the next class, I will show you some practical applications where I will show you some crystals that have some real crystals that looks like this, and you'll see how they are being studied, and possibly we would even try calculating total energy of different systems. We would some graphs that we have that looks abstract, we are going to do them practically, and you're going to see that what we are doing, though so far it looks very abstract, but they are applied in many systems. So when we talk about a cube, one of the things you talk about in property of the cube is to say, what is the volume of that cube? And the simple answer is to say that length cubed. When we say a cuboid, what is the volume of that cuboid? You say length times breadth times height to say the volume of a cuboid. But in this case, when we are talking about a three-dimensional figure, where the figure is bounded by vectors, since the figure is bounded by vectors, then a good way to calculate the volume is to calculate the scalar product, which is A1 dot A2 cross A3. So it's going to give you vector VA. So we'll be calculating hopefully in the next class. So Wigner's set cell. Wigner's set cell. Let's quickly talk about Wigner's set cell. An easy way to talk about Wigner's set cell is to look at this point and look at this, take a central point and say, this particular point, we can say, fine, you've been talking about this to mean a unit cell, this to mean a unit cell, this to mean a unit cell. But it's also good for a point to know its own territory, to have its own boundary. When you look at this shape here, I can also redraw this shape as something like this. If I draw with good accuracy and precision, the squares I have at this corner, the area of each of these squares will be equal to the area of each of these squares. So since the area of each of these squares is equal to the area of this square, so I can tell you that from since the distance from this point to this point is, we call it the lattice constant A, then at this point, this corner to this corner should also give us A. So, but within this cell, one thing you will notice that it is containing one lattice point. The same thing applies to this point. It's this region, it contains one lattice point. So each of the region contains one lattice point. So it is easy to visualize how the unit cell looks like. And that takes us to one of the fundamental property of a unit cell. A unit cell is said to have one lattice point. So this is a unit cell. It has one lattice point. And so a Wigner's set cell can be said to be a unit cell, so that every point within that cell, every point within this cell is closer to this point than any other points on this in this lattice, or this array of lattices. So this particular point, everything within this region is closer to this point than any other point. So, and that is like a simple definition of a Wigner's set cell. And a Wigner's set cell is a primitive cell, a unit cell, and it contains one lattice point. So if I say this contains one lattice point, and I said it's having the same area as this. How? Does that make sense? When you look at this closely, when if I should ask, how many lattice points do we have in this particular region? Can somebody answer? Somebody should try. How many lattice points do we have in this region?
1, sir.
Who is that person that spoke? Who is that person? What's your name?
4, sir.
Daniel
Paul.
Eshofuna, sir.
Daniel Paul. Okay, so can you tell us why are you saying 1 and not 4? Because I can see 4.
And it is because an edge resembles a quarter. So by the time we add
thank you.
We have 1.
Thank you so much. So you can mute yourself. Each of these points, this particular point is contributing 1/4 of its value to this region. It's contributing the other 1/4 to this region, and it's contributing another 1/4 to this region, and the last 1/4 to this region. So since this particular point is contributing 1/4 to this region, this particular point is also contributing 1/4 to the region of interest. This particular point is also contributing 1/4 to the region of interest. And the last point is also contributing 1/4 to the region of interest. When we add the 1/4s, 4 1/4s together, we have 1. We have 1. And that 1 is, that 1 means that we have 1 lattice point within this region. 1 lattice point within this region. So the same thing applies to when we are talking about a single line. We can say this point, if we want to cut the, okay, let me leave this place and let's have on a single line. If we should have a single line having points, as good as we can say here to here is A, here to here is A, here to here is A, we can also say this point to this point to this point is A. And we can also come to say that this particular point is contributing half to the left and also contributing half of its value to the right. So, and I expect you to take note of that for the future. So just like the example I gave about Wigner-Search cell earlier, talks about like a square lattice. When a square lattice, this is like a square lattice where we were able to say this is 1 lattice point. But in the case, this is very straightforward because the atoms or the lattice points are, they form a square pattern. But look at this figure 4a, where the lattice points do not form a particular square pattern. A way to go about it is to say that this is the central point. We want to determine the Wigner-Search cell of this particular at this particular point. So the Wigner-Search cell, like I've defined, as a locus of points that are closest to the central point, that is the central point of interest, than any other cell. So everything we have shaded here is closest to this central point than any other lattice points in this array. So a way to go about it is to say that from this point, the nearest neighboring lattice points are this 1, 2, 3, 4, 5, 6, 7, 8. So between this particular central point and the first one, we find the midpoint. We find the midpoint of each of them. So like this one now, from this point to this point, this is the midpoint. And at the midpoint, we insert a perpendicular bisector. And when we come to point 2, this is the midpoint between the central point and point 2. We also insert a perpendicular bisector. We also come to check point 3, the midpoint between the central point and point 3. We put a perpendicular bisector. We also come to point 4, the midpoint, we determine the midpoint. We also put a perpendicular bisector. So, perpendicular bisector in the sense that the bisector is having an diagonality with the line joining the central points and the neighboring points. So like that, and on and on. So having gone through the 8 points, finding the midpoints between the 8 neighboring points and that central point, and inserting perpendicular bisectors, the smallest polygon you can have is what, in a 2D plane, is what is called the Wigner set cell. So also when we move ahead to the 3D structures, you can see the shape is now getting more complicated. And if I should ask, what is the name of this shape? The best answer you can say it's resembling a small leather football. But all the shapes have names. They have names, and very soon, possibly in our next class, we should talk about them. So I think I should stop here. So next class would start with 2D lattice types, and I hope by next class we should conclude everything we have to say about crystal structure. Do we have any question before we leave?
No questions, sir.
You have spoken for yourself or the whole class? Okay.
Oh, myself. Oh.
Okay. Okay. See you next week. Bye-bye.
So what about the test?
Thank you, sir.
What about what?
Yes, sir. When is the test going to hold?
When is what?
Like the test, sir. When is it going to hold, sir?
I don't know.
Hello.
Hello?
Yeah. Hello, yes, sir. Can you hear me, sir? I said, when will the test hold, sir?
I said I don't know.
Okay, sir. Okay, sir.
Okay.
So should we be expecting the recorded class on YouTube, sir?
If it records properly, I will.
All right, thank you, sir.
So stop share. Turn this off.